say no, compoundness is the key to axiomatics, and you will see measurement and classicality will arise from that. It's also very different. In most foundations of physical approaches, you sit in the classical world and you look at the quantum world. Here this will be the dual. We axiomatize the quantum world and we will see what about the classical world from the perspective of the quantum world. So from the perspective of the physical system, how are we? So, and for some reason it makes a lot of sense when you do the mathematics. So, okay, so my first theorem is practice in physics is metric monoidal category. So,
sorry, can I just be clear about something? When you say we can see the classical world, does that mean you're going to add something that is not quantum mechanics?
I'm going to add, I will first axiomatize the quantum world, so I will get a very simple mathematical axiomatization of quantum mechanics, and then I'm going to ask, how can we specify that something is classical? And I will do that, and that will give me measurement structure. But I'm not going to say yet, I'm not going to reveal yet what this little bit is which I had to specify. Typically you say, everybody talks about quantification, I'm going to talk about classification. How do you say that? Classification. Something like that. Classicalification. Classicalization. Classicalization. I'm not living that long in Britain, yes, so my English is really rubbish. So but that's what it will be. Instead of specifying what's different about quantum mechanics, we will specify what's particular about classical mechanics. And it will turn out that the quantum structure is a really easy one, and things become more complicated. It seems that the classical structure is actually much more involved than the quantum one. That's not new. That's something which people in logic have been discovering over the last 20, 30 years. That there are much simpler logics than classical logic. And actually these logic tend to go quantum mechanically. So I'll talk about it. So first of all, my first level of abstraction is the admittance that there exist different kind of structures, which are different kind of systems which I give different names. Like for example, electron, qubit, classical data. These are clearly different things, and I want to give them different names because they are different. That already goes away from anything I know in physics. Just that mere assumption. To formally start from that observation that there are different things in physics, which you want to give different names. I haven't seen that anywhere yet. It's amazing. Like computer science people do this all the time. How do you the thing about people, the thing which I learned about computer science is like, you can't just go to a room full of scientists and start relying on their intuitions. Because of course everybody here clearly has these intuitions that there are different things. To a computer you have to say it explicitly. Because a computer is not going to invent it that there are different things. You have to say it. So, and actually by having to talk to a computer when you program it, you sort of learn better what you're doing implicitly without making it explicit. So it's just as simple as... So anyway, then you've got operations or experiments on a system which could be a preparation, an active force field, a measurement, all these different things. And you say for example, a measurement is something which applies to a quantum system and produces quantum together with a classical system. Classical system being the data, quantum system being the collapsed state. So you've got things, and then some of these things can be composed if their types match. Everybody sees what I mean by if the types match, it's obvious. Like the thing you act on, an operation has an input type and an output type. It means like it can act on something of this kind. Like for example, cutting a carrot only applies to a carrot. It doesn't apply to a car. It's as simple as that. So actually everything what I'm saying now applies to cooking. So you can compose operations. Like for example, if you cut your carrot, then you can sort of make carrot soup. So this first operation could be cutting the carrot to pieces, and this means then making carrot soup. But making carrot soup applies that you have cut your carrot to pieces. So these types reflect something about the stages of operations you've been through. So then there is something which you assume to be doing nothing operations, and this is category.
But why symmetric? Why do you need symmetric?
The composition.
Yeah, you said symmetric monoidal category.
Oh, we're not there yet, eh?
No, I know. I'm just thinking about it.
This is not symmetric at all. Actually, I have to comment about it. But, so at the moment, we just have category. This is the definition of category for those who don't know. So you've got types, you've got composition. It's as obvious as it is. There is nothing difficult about it. It arises everywhere in the world. Like universe exists of categories. Like interacting with something is just a category. It's as simple as that. And so, okay, here's the thing. So basically, there is something else. Sometimes you want to consider two things as one. For example, you've been cutting your carrot, you've been cutting your pieces of meat, and if you want to make your soup, you have to consider both the carrot and the pieces of meat, and do the operation of mixing them together in the water. So you want to have an operation which tells you, I have something of one type and something of another type, and now I'm going to conceive them as one whole, so that I can apply an operation to the whole thing. So that's this symbol. That's how the tensor comes in, just as a symbol of writing something down at this stage. And so I've got operation, so I can combine two separate operations into one. It's just applying something here, applying something there, and I conceive it all. But then you've got also like these mixing operations, just blending them into a big soup. And this is an operation which you can't sort of factor anymore in two, because it mixes up the things. So it's normal that you want this. Now it becomes really difficult. So, however intuitive it seems what I've been telling about, if you formally want to write down what it actually means, all the intuitions, it's all intuition what I've been telling. If you formally want to write down, this symbol should interact with my composition symbol, it becomes extremely complicated suddenly. Just writing down the obvious things you intuitively assume how these two should interact, I'm going to give some examples, is going to fill a couple of pages. And becomes a big, involved definition. And that's the definition of a symmetric monoidal category, basically. Just making these intuitions about how these two symbols, these two dimensions here, this is really dimension. In category theory they call this higher dimensional category theory. How these two dimensions will interact becomes very complicated. And that's where there is this amazing result that all these definitions you have to write down can be equivalently represented in like a very simple topological graphical calculus. So you don't have to remember them, because there is a picture calculus which incarnates all these assumptions you will do with them. So this would be an identity. This is a process from A to B. So what is in the box is like doing something. It's like an instruction. So this is composition of two. This is tensor product. You see how innocent it is? Just putting two things next to each other. Tensor. This would be a tensor with an identity. And these are like some operation like mixing, which involves two types. And so you see, this is completely intuitive what I mean by this. So basically, if you formalize this idea of these two dimensions, then you end up with something like this. This is a result, and this is a 60-page paper by two really big mathematicians, Joel and Street, somewhere in the 90s. Very recent, to say that the definition of such a thing can be nicely represented by pictures. Somewhere in the 90s, I think 92 or something. So this is really hard to prove. It's really, it's extremely tedious, basically. It's extremely tedious. So I'm just going to give some examples of the rules. Like this is one of the laws you should have to write down. This is a commutative diagram, but actually it just means this is called bifunctoriality. Bifunctoriality means I've got two things here. If I act here and then I act there, it's the same as